There it is. Sorry for the delay. Apparently I still had, Zoom's got this weird thing, if you haven't saved the previous file, even though you closed the session, it won't let you in. And apparently I had done that. All right, so sorry for the couple minutes behind, but we are here now, ready to kick off back into 6.2, the sum and difference formulas. And where we left off was right here, with example 4 already written down, and these A, B, C scenarios. Before we do that, just going to quickly scroll up to the formulas that, again, I've said these 2/4 you have to memorize. The sum cosine formula goes cosine, cosine, sine, sine, where the plus minus pattern swaps. The sine of a sum goes sine, cosine, cosine, sine, where the plus minus pattern is the same. The tangent formula, I said I would give you everything except for the sine. So I'm going to provide a short formula sheet for test 2 as well as the final, and you just wouldn't have what I'm covering up right here. You would have to remember that particular aspect. I think that's more than fair since most trig teachers make you memorize that formula too. But admittedly, as we will discuss in the problem we're about to do, after I cough, excuse me, is that this formula is completely avoidable. This formula is completely avoidable by doing something else. It might take a little longer. It might be a little less time consuming. It might be a more challenging or less challenging problem. But per usual, there's alternate ways to get jobs done. Okay, so back to the example. We said, given that the sine of alpha, some first angle, is 4/5, so there's its opposite over its hypotenuse as a reference triangle. And we mentioned that alpha is in quadrant 1, which means the reference triangle would be the actual angle, the actual triangle. And then sine of beta is 7/25, so there's its opposite and hypotenuse for a reference triangle and reference angle B. And that would definitely be referenced because beta is in quadrant 2. So again, what I'm saying is somewhere alpha is in quadrant 1. Here it is. I don't know the number. And then beta is somewhere over here. So it would be this angle right there would be your beta. Alpha would be that smaller, just the red angle. Now, because beta is in quadrant 2, that means its pluses and minuses are affected by a smart trig class. So we'll have to take that into account when we start doing the evaluations from the formulas. So we're going to find all three of these: sine of the sum, cosine of the sum, tangent of the sum. I could certainly ask for any of the sines, cosines, or tangents of the differences. It would be a very, very, very similar problem. But I just want to have good practice with the 3 different formulas. So I said, here's the thing you want to do. You can't find out what alpha or beta is without a calculator, and this is a no calculator concept, because it would be some goofy angle like, I don't know, 63.9528 blah, blah, blah degrees, not just 30 degrees or 45 degrees or 60 degrees. So you want to draw up little right triangles for these appropriately. Now, I did say that these are reference triangles. However, I'm going to go back and I'm going to erase the prime on the alpha, because as mentioned, alpha is in quadrant 1, which means this would not be a reference triangle. You can call it the actual angle. It's not wrong to call it a reference angle, but it's more appropriate as the actual angle. This one has to be a reference angle because with beta in quadrant 2, it's bigger than 90 degrees. So this is not an accurate portrayal of beta, but we could put its reference angle right here. That would be beta prime right there, just that little black section. All right, so first of all, we're probably going to need to find the adjacent sides of these angles by doing Pythagorean. So we can say that, let's call this just A. Do you want to call it A? Yeah, and then we'll call this one B. Your A would be equal to the square root of 5 squared minus 4 squared. After you've done this Pythagorean dozens of times, you just kind of start to memorize, I feel like, the different variations of the formula. If you don't like starting out there, then start with a squared plus 4 squared equals 5 squared and do your algebra to get there. That's up to you, however you want to get it done. Well, 5 squared is 25, 4 squared is 16, so that's the square root of 25 minus 16, which is the square root of 9, which is 3. So this is the 3, 4, 5 triangle. B, again, would be the square root of the 25 squared minus the 7 squared. You can always find a leg by doing square root of hypotenuse squared minus leg squared. All right, and 25 squared is a pretty big number. If you just wanted to save some time, we'll do it with the calculator. But again, this is no calculator material. You should be able to handle 25 times 25 on your own. So that's 625. And then minus 7 squared is 49. And then if you do 625 minus 49, you'd get 676. And in the interest, not 676, 576, geez. 576. And then you could go and try and find all your square roots under a normal method of just going 20 squared. That's 400, so it needs to be bigger. 22 squared, well, it's going to be bigger. At the end of the day, you'll figure out that that's 24. Now again, if you have a calculator, if you're allowed a calculator, which test 2 you're not, you could just go square root of 576. There you go. But this is, while kind of pushing the boundary of where I would ask you to understand your square roots. I don't really go into 3 and 4 digits with them. This is achievable just by, like I said, trying 20 times 20 is 400. So go bigger, maybe 22 or 23 or 24 until you get it. Hold on one second. All right, so our B is 24. So I happen to give you 2 triangles with only integers, only whole numbers. That's kind of cool. At least it means there's no radicals in the answers anywhere, but it would have been perfectly fine if there were. Now let's get to the actual problem at hand. Finally, A is the sine of alpha plus beta, the first plus the second. So using that formula from above, it goes sine, cosine, cosine, sine. Sine of alpha, cosine of beta. I'm going to skip the plus or minus for a second, and then cosine of alpha, sine of beta. Again, get to work on that memorization. Then if you remember, for the sine sum formulas, the plus or minus takes the same as the original one. It's cosine that swaps them. It's cosine that swaps them. Now you might say, well, I don't know what alpha is, so how do I find its sine? I don't know what beta is, so how do I find its cosine, etc.? Well, 2 of them were actually given to you in the problem. You were told what sine of alpha and sine of beta were. Did I do both sines? That just doesn't sound right for my original problem. I did. Okay. I'm just making sure that I didn't write anything wrong. Would have been a much worse scenario if I found that out later. All right. So we don't have to know what alpha is to find sine of alpha. That's what these right triangles were for. So the sine is the opposite over the hypotenuse. And again, it just so happened to be that we already knew the answer. It's 4/5 because we were told it's 4/5. But I can also figure that out by going opposite over hypotenuse for the alpha triangle. Then that's times the cosine of beta. So we're now on this triangle. Now we're doing a cosine. Cosine is adjacent over the hypotenuse. So 24 over 25, and I'm going to do this in red for a second. Red for wrong. Why is that wrong? Why is it not 24 over 25? Because as a reminder, beta is in quadrant 2. It's over here. Quadrant 2, the pluses and minuses for sines, cosines, and tangents can change. Sines are positive, cosines are negative, tangents are negative. So because we're dealing with a cosine, cosine is negative in quadrant 2. So we're going to want to make that little note somewhere. So that's why this 24 over 25 is wrong, because cosine is negative in quadrant 2. 3 exclamation marks. It's amazing, not undo. Why did that just circle? That's all right. So the cosine of beta is not going to be 24 over 25. It's going to be negative 24 over 25, because beta is actually in quadrant 2, so we have to give the cosine a negative for the beta. That little detail, if you get that one plus or minus wrong, the whole thing is wrong, and that's going to frustrate you to no end. Now again, test, you can say, Mr. Beckner, look at problem 17, see if I can get some partial credit. And then if you make one boo-boo and the rest are right, then I can give partial credit, but I'm not going to give full credit. All right, so now we're here, we're at the cosine sine. So cosine of the alpha, cosine of alpha is 3/5 adjacent over hypotenuse. And you might go, oh, it's negative 3/5. No, it's not, because alpha was in quadrant 1. Beta was in quadrant 2. So everything's positive in quadrant 1, so it is just 3/5. The cosine of alpha would be 3/5. No negative, because alpha is in quadrant 1. Little details to keep track of, just like real life, times. Now we're going to do the sine of beta. Now again, you might say, oh, this is negative and then 7/25. That would be wrong, because sine is positive in quadrant 1. Remember, a smart trig class. Why is that? Because sine is based on the y value. In quadrant 2, you're going up, so y is positive, so sine is positive. So it is a positive 7/25. And then from there, we're just going to simplify our arithmetic. Let me go down here for space reasons. If you have any reduction, go ahead and reduce it, but you don't. 5 times 25 in both bottoms is 125. Let's leave our plus sign. 4 times 24 is 96, so that's negative 96. 3 times 7 is 21, so that's positive 21. Keep the denominator of 125 for now. Negative 96 plus 21 is going to be 75. This is obviously reducible. 25 will go into both of those 3 and 5 times, respectively. Sorry about that. You heard it. I need to make sure that's... Sorry, if I don't see a package person walking away, I have to make sure it's not someone important. It's just someone who wants to mow my grass. That's okay. All right, B, not B, yes, B. Isn't teaching from home fun? All right, so next up was the cosine of alpha plus beta. So before I get to the triangles, let's set up the formula. So again, memory. Cosine, cosine, sine, sine. So cosine alpha, cosine beta. I'm going to skip the plus or minus for a second. Sine alpha, sine beta. For the cosine sum or difference formulas, the cosines are paired, the sines are paired. For the cosine formulas, the plus or minus aspect swaps. So that's going to be a minus between them. Okay, well, we already saw how A went, so B is going to go pretty similarly. We just got to find the sines and cosines of the respective angles, but we have to be careful with beta, because beta was in quadrant 2. Any cosines or tangents, which you don't see, would be negative. Everything with alpha is positive. The sine of beta would be positive. It's just a cosine of beta that'll be negative, which we do have a cosine of beta again, so that's going to be the negative one when we get there. All right, so cosine of alpha. Let's scroll up just a little. Adjacent over hypotenuse, 3/5. There is your cosine of alpha, adjacent over hypotenuse, times. Cosine of beta. So beta prime's cosine is 24/25, but it's negative 24/25 because cosine's negative in quadrant 2, because we went left and x is cosine. Then the minus from the formula. And then we have sine alpha, sine beta. Sine of alpha is 4/5, opposite over hypotenuse, times. Sine of beta will be 7/25. And then we just clean up the arithmetic. All right, so 3 times 24, it's 24, 48, 72. So negative 72 over 125. Then minus 28, the 4 times the 7 over 125. Combine your denominators. Negative and a negative means add them. 72 plus 28 is 100. Keep the sign of negative. 25 goes into both of those 4 and 5 times, respectively. So the answer is going to be negative 4/5. Also, I think I was getting ready to type to write the negative in this when I got distracted by the person walking up. I had the negative here. I forgot to put it here. That was a little boo-boo. Thank you, distractions. Negative 3/5 was that answer. Negative 4/5 is that answer. Now you might say, well, Mr. Beckner, could you predict this plus or minus sign in the answer by knowing that alpha is in quadrant 1 and beta is in quadrant 2? And actually, no, you can't. Because while here was alpha, here's beta, if you want to see the combination of them, you just start from the end of one and draw the other. So if I start from the end of blue, and then I draw this angle again, which looks like about this, based on this picture, this whole thing looks like alpha plus beta, but maybe alpha was really, really teeny and beta was really, really teeny in quadrant 2, so this angle could have been up here possibly. So the sum and differences of problems like this, you can't tell if the original angle, if the sum or difference of the angle is going to be in quadrant 2, quadrant 3. You can kind of boil it down between two of them, but you're never going to be able to particularly pick it out. So no, I cannot just determine, oh, I know this answer is going to be negative or I know this answer is going to be positive. I can't. You have to do all the arithmetic in the process. It's the individual sines and cosines that you can say, hey, this one's negative because you're in quadrant 2 and cosine's negative in quadrant 2. All right, C. And this is going to be the tangent of alpha plus beta. So then we're going back to the tangent formula, which I said you don't have to memorize, just the pluses and minuses in it. But it does go tangent of alpha, then a plus or a minus, a tangent of beta, all over a 1, and then a product of those, tan alpha, tan beta. For this formula, we said that it keeps the same sign in the top, but it's the opposite sign in the bottom, and that's the aspect that I said you would have to remember. I will not put that on a formula sheet. Okay, so then we just go back to the triangles and figure out the tangents of alphas and tangents of betas. Now, we're in quadrant 2 for beta, so this and this are going to end up being negatives because we're in quadrant 2. So up here we said cosine is negative in quadrant 2, also tangent is negative in quadrant 2. A smart trig class. S says sine is the only positive one in quadrant 2. Again, not talking about secants, cosecants, cotangents, just sines, cosines, and tangents. All right, so tangent of alpha, I'm going to just kind of do this for a moment so you can see everything. Tangent of alpha is opposite over adjacent, so that's 4 over 3. Opposite over adjacent is tangent. And plus, tangent of beta, opposite over adjacent is 7 over 24, but negative because trig. Then all over 1 minus the tangent of alpha we already said is 4/3 times the tangent of beta we already said is negative 7 over 24. The trig part is shorter for this, but the arithmetic is going to be longer. All right, so buckle up. Now, in the tangent problems we did earlier, there were square roots everywhere, so we were having to rationalize things, then rationalize them again. There's no square roots here, so that's out the door. Just combine the top, combine the bottom. There's an alternate way you can simplify this fraction by just finding the individual LCD and multiplying that out. But first, you got to actually do some processing. So let me fix up that bottom. That's 4 over 3 minus 7 over 24, then all over 1 plus, because of the double negative. Nothing, well, it does, yeah, I'll reduce it. 4 and 24 will reduce to a 1 and a 6. And that's the only reduction that's going to happen. Then you multiply straight across, and you would get positive 7 over 3 times 6 is 18. Why does that sound wrong? So that's positive 28 red. 28 over, oh, I know why that sounds wrong. I said you can't reduce anything else. Oh, no, I didn't. I multiplied the top wrong. That's what I'm doing wrong. I canceled the 4. The top is just a 7. There we go. And then the 3 times the 6 was the 18. So 7/18. All right. Well, either way, you got to find an LCD, which is going to be a pain in the butt for all of this. For the top one, your LCD is going to be 24. For the bottom one, it's 18. So we can say, all right, well, I need to multiply this one top and bottom by 8. So we're going to take the 4 over 3, and we multiply top and bottom by 8. Then the minus 7 over 24, that's already good. Then all over. The 1 is obviously going to have to multiply top and bottom by 18. So it gets the LCD in the bottom. Then minus the 7/18. So 8 times 4 is 32. So you get 32 over 24 minus 7 over 24. Then all over. 18 plus, so 18 over 18 plus 7 over 18. 32 minus 7 in the top fraction parts is going to be 25, so that's 25 over 24. And then that's going to be all over, the 18 plus the 7 is a 25 over 18. This is a division of fractions, so you can change it to multiplying the reciprocal. That's 25 over 24, that's the top one. Then a times instead of a division, and we'll flip the 18 and the 25. The 25s end up canceling, because you got one in the top and one in the bottom. So you end up with 18 over 24. Oops, wrong color. But 6 will go into both of those. 6 will go into 18 3 times. 6 will go into 24 4 times. And amazingly enough, you get another super simple answer of 3/4. No one wow, my 3s are awful today. There we go. No one probably would have predicted that answer was so simple, except for the fact that the sine and cosine were simple, so maybe tangent would be simple. That's the only thing I could base that off of, just personally. I want to admit this was not the only way to have simplified this problem. In fact, I chose it to do it differently than I normally do, just to remind us of multiple techniques. Doing the LCD in the top and the bottom, a lot of people won't do it that way. A lot of people just would have found the LCD between the 3, the 24, and the 18 all at once. And that would have been fine. 18's 2 times 3 times 3. 24 is 2 times 2 times 2 times 3. So you would need 2 2s and 2 3s. I'm sorry, I think I said the wrong thing. 3 2s and 2 3s, which would be 72. So you could just say the whole LCD is 72, and then you take 72 times the 4 over 3 minus 72 times the 7 over 24 all over 72 times the 1 plus 72 times the 7 over 18. All those individual fractions would then reduce, and you'd just have a single fraction adding and subtracting, and you can still get to the same answer. Again, it doesn't matter which way you do your arithmetic. What matters is that you know a way that works. So that problem, I think you can all agree, was much more challenging than the other two for a couple of reasons. First of all, the tangent formula is goofier, but at the same time, I don't make you memorize the whole thing, so that's kind of a give and take. Second of all, the arithmetic was more of a pain in the butt, but again, I do expect you to have this skill in your tool shed, your tool belt, whatever. Third, there's an easier way to do this. Remember, tangent of anything is sine over cosine. And we did the sine of alpha plus beta and the cosine of alpha plus beta already. So just divide these. Take the sine answer, take the cosine answer, divide the two things. So the answer from A was the sine, that was the negative 3/5. The answer from B was the cosine of negative 4/5. So negative 3/5 was the sine, negative 4/5 was the cosine. So let's say this is just negative 3/5 divided by negative 4/5, which again, fraction divided by fraction means take the first fraction, multiply by the reciprocal of the second fraction. You'll see the 5's cancel, the negatives cancel, the 3 over the 4. Holy cow. Easy button. Easy, easy, easy. This is only easy if you already did the sine and the cosine. If I have a homework problem or a test problem that just asks for the tangent, well, you're stuck just doing the tangent like we did in that problem. But there are homework problems that ask for all three. I could give you a test problem that asks for all three. So if you have to do the sine and cosine, then I ask for a tangent, just go ahead and divide those two things. As we said, in trigonometry, there's almost always more than one way to get the job done for something. Very often, there's a dozen ways to do things. Right. So we're going to do another one of those problems, except we're only going to do the sine portion of it. But I know I've mentioned like every 2 or 3 weeks, I have to take a little 3-minute pause for something important. And this is one of those times. So I will be back in about 4 minutes. I wish I had time to go ahead and write the problem down. I apologize for this. Thank you for your patience. Take a deep breath. All right, thank you for your patience. We're up to example 5, last one for the section. All right, so I'm going to tell you this time that the tangent of alpha is negative 4/3, and that we are going to have this one not equals in quadrant 2, and that the cosine of beta, oh, I know why this looks funny, I didn't zoom back in. It's like I'm taking up a lot more space than I usually do. All right, we're gonna get it right now. The tangent of alpha was the negative 4/3, and alpha is in quadrant 2, like we said. And then we're gonna say that cosine of beta is equal to 5/6, and that beta is in quadrant 1. Now I could use angle references instead. I could say alpha is between 90 and 180, or between pi/2 and pi. I could say beta is between 0 and pi/2, or 0 and 90 degrees. Depends on what I want to ask for. So we're just going to do one of these, find the sine of alpha plus beta. And I could ask for the minus, I could do the cosines or the tangents, also with minuses as well. We're just going to do one since we already practiced this pretty well last time. This is just going to help us get the concept down. So for alpha, so it says the tangent is negative 4/3, which says for a reference triangle, especially needed since we're in quadrant 2, especially noticeable since this is negative, that its opposite will be 4 and its adjacent will be 3. So when we start drawing alpha's triangle, first of all, it won't be alpha's triangle, it's alpha prime, because it's in quadrant 2. So its opposite's going to be 4, and its adjacent's going to be 3. I'm not even going to do the math this time. That means that this is 5. If you do the square root of 3 squared plus 4 squared, you'll get 5. Show that on your own if you have to. So for the beta triangle, the cosine is 5/6, so that's adjacent and hypotenuse. Now beta is in quadrant 1, so this is a regular beta, not a beta prime. Its adjacent is the 5, its hypotenuse is the 6. I will show the work here, so let's call this side B, and B would be the square root of 6 squared minus 5 squared, which is the square root of 36 minus 25, which is the square root of 11, and that's not simplifiable. So that side, that leg, is square root of 11. All right, with those two reference triangles, we are good to go, except I do want to go ahead and mention, again, alpha being in quadrant 2, means that some of your trig functions are going to be negative. Quadrant 2, cosine and tangent are negative. That's me saying that right here. Cosine and tangent, that's cosine comma tangent, are both less than 0. They're both negative. So in our formulas, anytime we do a cosine of alpha or a tangent of alpha, we'd have to make them negative. Well, the nice thing is that was basically told for us there with the tangent, but the not nice thing is I didn't ask you for a part C with the tangent formula. Tangent's not even used in these. All right, so we're ready. Sine of alpha plus beta. Deep breath. Sine formula, memorize it. Sine, cosine, cosine, sine. The plus minus pattern is the same as the original one. Cosine's the one that takes the opposites. Then we just use these. So for sine of alpha, that will be 4/5. We're in quadrant 2. Sine's positive in quadrant 2. Cosine of beta would be the 5/6. That was even given to us. You don't even have to think that through if you pay attention. And then the plus symbol. And then now we have the cosine of alpha, which for alpha prime, its cosine is 3/5. That's alpha prime. But we're in quadrant 2 for alpha, so the cosine's negative, like we said earlier. So I need to do this. That subtle little detail will change everything, and it usually makes the numbers much worse. All right, then times the sine of beta, so we're over here at beta. Sine of beta is square root of 11 all over 6, so times square root of 11 over 6, quadrant 1, so no worries there. If we had been in, say, quadrant 3, the sign would be negative. If we had been in quadrant 4, the sign would be negative. Both signs, that is to say. All right, so let's go down here. So I got some space. Let's multiply straight across, reduce. The 5s will cancel. The 4 and the 6 would reduce to a 2 and a 3 if you do it that way. But I'm not actually going to do it that way, because in this one, if you reduce the 3 and the 6, the bottom, that just turns into a 2. Nothing else reduces. So this denominator is going to be a 10. And then this denominator is going to be a 3. And then you'll have to go and get an LCD since you got to combine this stuff. So this is going to be one of the few times where I'm going to say, don't actually reduce this. Just go ahead and leave them, since the bottoms, 5 times 6, 5 times 6 will be the same. So I'm going to multiply without reducing. And again, this is atypical for me. 4 times 5 is 20. 5 times 6 is 30. But that was, again, just to save some time. Minus 3 times square root of 11 is 3 times square root of 11. Over 5 times 6 is 30. Again, see, doing it this way, I have my LCDs already. They already match. If I had reduced, the denominators were going to be a 3 and a 10, and then I just got to build them up again. It would have been going around in a circle. Now, maybe you don't see that and you go around in a circle, but that's not the end of the world either, as long as you know how to get an LCD. And then while this is not an acceptable answer as a split fraction, if you combine them, it won't be reducible. So this is your answer. Nothing reduces here. Oh, 10 goes into 20 and 30. Yeah, but not 3. Oh, 3 goes into 3 and 30. Yeah, but not 20. Remember, you got to reduce with everything when it's a combined fraction. So that's one good answer. I'll show you the other good answer if you took the 20 over 30 minus the 3 square root of 11 over 30 and reduced it. The zeros, the 10s cancel for the 20 and the 30. The 3s cancel there, leaving a 10 in the bottom, giving you 2 over 3 minus the square root of 11 over 10. That minus kind of ran on, didn't it? There we go. That is also an acceptable answer, but if you wrote 20 over 30 minus 3 squared of 11 over 30, these separated fractions without reducing it this way, that would not be an okay answer. This is not okay, but this is, and this is. Don't care which way you write it. Sometimes one's better than the other, but they're both right. All right. That is 6.2. That was a weird noise. Wonder if y'all heard that. It sounded like blinds breaking, but it wasn't. I don't even have blinds in this room. So that's 6.2. Remember, this test coming up is only going to be 4 sections: 6.1, 6.2, 6.3, and 6.5. So we're going to do 6.3 next. We will be skipping 6.4. I already mentioned that I will upload some notes that would go with that section when we get to 6.5. But I won't test you on it. There's no homework on it. It's just possible that when you get to calculus, you might need one of those formulas here and there, and it would have been cool to have used them before. But the thing about formulas and applications of calculus is they're just formulas. It's just plugging numbers into things. So the idea at this level of algebraic and trigonometric skill is that if we can give you one kind of kooky crazy formula and you understand how to use it, we should be able to give you any kooky crazy formula and you be able to understand how to use it. But it's just not in our syllabus, so we don't cover 6.4. But again, it's not to say that those formulas are not important and are never used. They're absolutely used in calculus. They're absolutely used in trigonometry. I just won't test you on it. All right, but I know if I was the student, I would have liked to have seen it first. 6.3, double angle, half angle. All right, so we got that. that. I already hit enter a bunch, so that should be fine. Double angle and half angle formulas. So I'm going to write down a few formulas, a few double angle formulas. I'm going to prove one or two of them based on how much time this takes. And then I'm going to take one of them and show some variations to it. But I'm probably getting ahead of myself. Let's just go ahead and write those three formulas down. So here are your double angle formulas. The sine of 2 theta. So double angle means that inside you think you're dealing with twice an angle you're used to using. That's what that means. A double angle formula means the inside is twice an angle that you would know how to handle. So let's say you know how to handle 30, but you forgot how to handle 60 and you're looking at 60. So you see 60, well, you could just go, well, that's twice 30, and I know how to handle 30. So then you could apply this formula. Now again, it doesn't seem that useful there, and admittedly it's not because you're supposed to have memorized 60. And in most situations, the angle that's doubled is even, how do I want to say this? The halved angle might actually be the complicated one. So admittedly, this one's not used that often to actually find a trig numerical answer. This formula is much more often used to simplify equations, to do calculus with things. This one is extremely important. And the formula is, it becomes 2 times the sine of theta times the cosine of theta. It's almost like the 2 pops out, and then as a result, you get a cosine as well. You've got to memorize this one. Next up, we have the cosine of 2 theta, which this one is going to have 3 versions. The initial one that I'm going to write is cosine squared of theta minus sine squared of theta. So this almost looks like Pythagorean. It almost looks like sine squared plus cosine squared, except I have these swapped and there's a minus there. So it's not Pythagorean. So again, there are 3 versions of this that we will get to the second and third in a little bit, not yet though. Let's not do too much at once. And I'll spoil it. The other 2 versions of this are just by changing cosine squared to 1 minus sine squared or sine squared to 1 minus cosine squared, just using Pythagorean. All right, so finally we have the tangent of 2 theta, which is 2 tan of theta and all over 1 minus tan squared of theta. All right, so I'm going to leave some room over to the right of this for the cosine 2 theta variations, but I'll come back to that after we do some fun proofs. So let's do the sine of 2 theta proof. We'll start with that one. We're going to prove this formula. Now you might be saying, Mr. Beckner, you didn't prove the sum and difference formulas. Why are you going to torture us on this? The sum and difference formulas take significantly longer to do. It involves a lot of graphing. It's a bit of a headache. You have references, textbook, internet that you can go and find it if you want to see the proof. We just said we didn't have time. This is a much shorter proof. And cool thing is, we're actually going to use the sum and difference formulas to do this. So here's the proof. Let's take the sine of alpha plus beta formula from the last section. But what we're going to do is we're going to call alpha and beta the same angle, and we're going to make them theta. So if alpha is 20 degrees, beta is 20 degrees, and that makes theta 20 degrees. I'm just saying they're all the same value. I'm deciding to make them all the same value because I know that's going to be a constructive idea in the proof. Again, proofs are very often trying 10 million things until you find the thing that works. but we're not going to try the 10 million things. We're just going to go straight to the thing that works. Finding an actual proof of math requires a lot of insight, thinking outside of boxes, trial and error, patience. Following a proof just requires being able to follow the algebra and trig along the way. So this is going to work though. So the sine of alpha plus beta formula, which went sine of alpha cosine of beta plus cosine of alpha sine of beta, we're just going to call all the alphas and betas thetas. So again, what used to be, I'm going to erase this, sine alpha cosine beta plus cosine beta sine alpha. It's just all of those are going to turn into thetas, 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 thetas. Why am I doing this? Because I can write the sine of 2 theta as the sine of theta plus theta. So that's why we decided to call alpha and beta the same angle, because now the first one is like our alpha and the second one is like our beta. And then we just go sine of alpha cosine of beta cosine of alpha sine of beta. So that's the sine of theta times the cosine of theta plus the cosine of theta times the sine of theta. Again, previously these were alphas and these were betas, but we called alpha and beta theta. Isn't that great? I'm sorry, I'm terrible. Why did we do this? Well, sine, cosine, cosine, sine with all the same angles in them. This term is exactly the same thing as this term, except I wrote sine and cosine backwards. So just to make this look a little better, sine theta, cosine theta, then plus sine theta, cosine theta. This is like xy plus xy, which is 2 of the xy. So it's 2 sine theta, cosine theta. And that is QED. We proved the formula. The left side matches the right side. It's not the end of the world. Next up, let's do the cosine proof. So again, we're going to take the cosine of alpha plus beta, but we're going to call the alpha and the beta theta, so that we can call cosine of 2 theta cosine of theta plus theta. So that's cosine of 2 theta is really the cosine of theta plus theta. 2x is the same as x plus x. We're just deconstructing it. And then that's a first angle. That's a second angle. So that's like the alpha and the beta. We just apply the formula. It goes cosine, cosine, sine, sine. So cosine of the first times cosine of the second, which just happen to match. Then sine of the first, sine of the second, which also match. Now the pluses and minuses swap here. Since that's a plus, this is a minus. Well, that's x times x, which is x squared. This is y times y, which is y squared, but they're not x's and y's, they're cosines and sines. So it's cosine squared minus sine squared. And that's exactly what the right-hand side of the formula says. So QED, we're done. It's just simple algebra and trigonometry combined, knowing what to do to construct the proof. Again, if I asked you to create this on your own, you might try 10,000, 10 million things before you figure out what to do here. I can't tell you how creative and constructive you are. But again, I'm not asking you for that necessarily. But if you are going to go into advanced math and engineering, this is the type of foresight and processing that's a good skill to have. Yeah, we'll do the tangent. We got time. So the tangent proof. We're going to say that the tangent of 2 theta is equal to the tangent of, you guessed it, theta plus theta. No zeros there, just getting a little sloppy. And this formula was tangent of alpha plus tangent of beta. So tan theta plus tan theta over 1 minus tan alpha, tan beta, but they're all thetas. Well, the top has an x plus an x, which is 2x, so that's 2 tangent of theta. The bottom has 1 minus tangent times tangent, so 1 minus tangent squared. There, we're done. Once you've done one, the other two just kind of fall into place. All right, how about the cosine of 2 theta variations that we have not written down yet? So we're actually going to figure out them and then show you. And I already mentioned this earlier that you're going to just use Pythagorean, but only replace one. So you're just trying to have everything in terms of sines or just everything in terms of cosines. So let's borrow that formula, which was cosine squared minus sine squared. I guess it was sitting right down there as well. So we had the cosine of 2 theta. Here's the original formula. It was cosine squared minus sine squared. So this time I'm going to replace the cosine squared. Cosine squared is 1 minus sine squared. So that would be 1 minus sine squared theta. I don't actually need the parentheses. I'm just showing it for emphasis. Well, you have a minus sine squared and a minus sine squared, so they stack and make a 1 minus 2 sine squared of theta. So this is going to be the right-hand side of the first variation, the second version of the formula. Or when you have that cosine squared minus sine squared, let's instead just replace the sine squared. So I'm not going to replace the cosine squared this time. I'm just going to replace the sine squared. This time the parentheses is important because of the minus in front of it. So I'm going to have to distribute that. You get cosine squared theta minus 1 plus cosine squared theta. Well, there's 2 of those, so that would give you 2 cosine squared theta minus 1. And that will be the right-hand side of the third version of the formula, aka the second variation. So let me just kind of pull back. So our variations were that cosine of 2 theta. The first one is the 1 minus 2 sine squared. And the other one was the 2 cosine squared minus 1. So there's similarities between these. They both have the other, one of them has a sine squared, one of them has a cosine squared. One it's positive, one it's negative. There's a 1 in there. There's a 2 in there. There's a lot of similar pieces. I actually don't want to tell you exactly what you have to memorize from this yet. I have my decision. It's the same decision I've made for the past couple years, but I don't want to tell you which ones to memorize yet because I want you to try and just kind of put most of these together on your own. I will give you some of these. I'll say I'm either going to give you 2 or 3 of these 5 things. But the point is, I don't need to give you these because if I give you this one, you should be able to find the other 2 doing that, just doing Pythagorean. That's a skill you should have. I don't have to give you any of these if I was a truly testing trig teacher, because you can find them all by doing all of this stuff. Again, these are all moving parts of the same machine. So we give you the 3 versions for the cosine because, again, for trig, honestly, they're mostly interchangeable. Notice I said mostly. But when you get to trig equations and calculus, it starts becoming an issue that one is going to be better than the other. If I'm just talking about evaluating angles, all 3 of these are perfectly fine. In fact, I would say these are probably better for evaluating angles because then you've only got to do a sine or you've only got to do a cosine. So I think these 2 are better for actual evaluations. But what's interesting is a lot of times when you're doing equations in calculus, this tends to be the better one. And again, I said tends to, and I'm not even going to say usually. I'm going to say like 51% of the time, and I might even be exaggerating there. Maybe like 40%, which out of 3, that would still be the biggest one, potentially. Okay, so I know we're all excited to use these, so let's try some else. For example 1, got enough space, got enough space. We're going to say if the sine of theta is equal to 5/13, couldn't read my own handwriting for a second there, and theta is in quadrant 2. I love putting things in quadrant 2. We're going to find A, the sine of 2 theta. I bet you're going to figure out where I'm going with this. B, the cosine of 2 theta. And you guessed it, C, the tangent of 2 theta. Now, once again, since I'm asking for sine, cosine, and tangent, you could just find the sine and cosine, divide them, and boom, there's your tangent. You don't have to use the formula. If I give you a problem and I only ask you for the tangent, it would be more efficient just to do the tangent. However, you could take the inefficiency, do the sines and cosines anyways, and divide them in an instance where, say, it's a test, you don't have any formula sheets available, or it wasn't on the formula sheet, and you can't remember it. Okay, well, I forgot the tangent formula. That's okay. Let me just do the sine. Let me do the cosine, divide it, boom, didn't even need the formula. All right, so sine of theta, I didn't give you a second angle because we're just talking about doing twice an original angle. And I don't know what this angle is. I have no way of determining this without a calculator and decimals, and ugly numbers. So we're not going to do any of that. We're going to do just like last time. We're going to draw up a triangle, a right triangle. Now theta is in quadrant 2, so when I do this, I'm supposed to write theta prime, and I do highly encourage you to know when and how to do that. Otherwise, you'll be missing some pluses and minuses somewhere potentially. Sine is opposite, so 5 over hypotenuse 13. And then you can call this leg B, which B is going to be the square root of 13 squared minus 5 squared, which is the square root of 169 minus 25, which is going to be 144, and the square root of 144 is 12. So that's the 5, 12, 13 triangle. I've actually given you several triangles in here with whole numbers, some weird versions of the, I already closed out of the file, but we had the 3, 4, 5 already. Here's the 5, 12, 13. And then what was the other one we did? It was the I don't know, time to remember what it was. Oh, the 7, 24, 25. That's what it was. All right, so here's our triangle that we're going to use for everything. So for A, can I fit it all here? I think I can, I think I can. Sine of twice the angle. You can't just take the 5 and the 13 and do 2 times that. Sine functions don't work that way. They're like logarithms in that they're unusual. You can't just magically pull this 2 out. That's why we just got those formulas. So you go, all right, well, I know theta, sine of theta was 5/13. Maybe the angle is 50 degrees, and now I'm asking for what's the sine of 100 degrees. And you go, okay, well, I don't have a triangle for 100 degrees because I don't have any of the opposites or hypotenuse numbers. But if I have the 50-degree angle numbers and stuff, again, I'm just saying this is 50 degrees, which is not true, then using a formula for this, knowing that, oh, well, sine of twice an angle is just 2 times its sine times its cosine. Definitely want to make sure they don't look like 2's now. Well, here is just the regular angle reference, so pluses and minuses might change. And then we're just going to use this triangle. That's it. You don't have to redraw this thing, figure out where it is, quadrant it's in, it's fine. But we do need to be careful. Remember, yeah, it's fine there. We said that theta was in quadrant 2. So that means, based on us smart trig class, smart, S, sine is positive, everything else is negative. So cosine and tangent are negative. You are going to lose a lot of points in your life if you don't write things like that down, or at least just have them in your brain permanently etched. All right, so that's a 2. The sine of theta is 5 over 13, and we're in quadrant 2, so it's positive. Times the cosine of theta is adjacent over hypotenuse, 12 over 13. But if you do this, it's wrong because we're in quadrant 2, cosines are negative. So make sure you give that bad boy its negative. The 13s square up to 169. Nothing's going to reduce. 2 times 5 is 10. 10 times 12 is 120. So we end up with negative 120 over 169. And that answer is not simplifiable. B, the cosine of 2 theta. Cosine of twice the angle. So again, if we're pretending this is originally 50, well, first of all, it's in quadrant 2, so 50's out. Let me go with 100. If we're pretending that theta is 100 degrees, so what I'm asking for is what's the cosine of 200? You go, well, I don't have a triangle for 200, but I do have a triangle for 100. Again, pretending this was the reference for 100. Pretending. So you go, well, let me just use the formula, of which this is the one with 3 versions. The sine 2 theta's only got 1 version. Cosine gets 3 versions because it had a cosine squared and a sine squared in it. Does not matter which variation you use. I will go ahead and point out that these are easier for example 1b, because you would only have to do a single trig evaluation, either the sine or cosine. But in the interest of practice, I'm going to do the original version so that we see the evaluations of both of them. But again, what you can go back and do is go back to example 1b and try it using this formula, try it using this formula, and everything should match up and be square. All right, so I'm going to use again, the first one, which was cos squared minus sine squared. We already know what the cosines and sines are. We just did them. Sine was 5/13. Cosine was negative 12/13. Again, negative because quadrant 2. So if you're squaring cosine, you just get negative 12 over 13 squared. And minus, square the sine one. Sine was 5/13, so 5 over 13 squared. All right, well, the negative for the first one's going to cancel. 12 squared is 144, so that's 144 over 13 squared we know is 169. 5 squared is 25, so that's minus 25. I was about to write this backwards. It's very weird. 25 over 169. And then you do 144 minus 25. That's going to be 139, 119. So 119 over 169, and it's positive. C. Now you might say, oh, okay, well, let's go to the tangent formula, which was 2 tangent over 1 minus tangent squared. So tangent for this problem is going to be 5/12 for the reference triangle, but we're in quadrant 2, so it's negative. So what you would be doing is you'd be putting negative 5/12 here, and you'd be putting negative 5/12 here, which it's going to be squared. So that bottom is now 1 minus negative 5/12 squared. And you got the 2 here, and you're going to have a fraction inside of a fraction and all that annoying stuff that we see every single time with the tangents. And it's frustrating. It's doable. I do expect you to have the skill to do that. However, since I already asked you for the sines and cosines, this would be significantly much more efficient to just remember the tangent of any angle is the sine of the angle over the cosine of the angle. So I'm just going to take the sine answer, which was negative 120 over 169. I'm going to divide it by the cosine answer, which is 119 over 169. If you do these 1,000 times, you'll start recognizing if you have matching bottoms, they're just going to end up canceling. Same with the tops, but I will show all the extra work. So this is negative 120 over 169, the top fraction. Change it to times. Flip the bottom fraction. I'll use color for that. So times 169 over 119. You see the 169s will cancel, and you just end up with negative 120 over 119, a much more efficient way to do it. Again, I would suggest, especially if you're rusty with that fraction math, as much as you don't want to do it, I know lifting that 50-pound dumbbell hurts, but if you want to grow and gain muscle, you have to lift it. So I know that doing this fractions inside of fraction math and clearing LCDs might hurt a little, hurt your brain this time, but your brain's a muscle. And if you want it to grow, you got to practice it. You got to do it. But on that note, we will call it a day there. There is absolutely no way I'm going to finish any of the next examples with 3 minutes to spare. I could do A, but not B, and I don't want to. So we will continue with this section when we pick up on Monday. Because we finished 6.2, that assignment will be due in 1 week, which is October 28th. So 6.2 is due 10/28. So yeah, so next time I believe we'll be able to finish 6.3, and then it's probably going to take us 2 full classes to do 6.5. So I'll start talking test dates once we begin 6.5, that I think I'll have a date knocked out by then. All right, so with that being said, if you have any questions, email me. Have a great weekend. Have a good day. Study hard, work hard. Email me with any questions again. I think I already said that once. All right, take care, everybody.